Hi, so I'm Andy Patterson. I'm a first-year PhD student here working with Martha White. Today I'm going to tell you guys a little bit about the placement of the importance sampling ratio, specifically for gradient TD methods. This is part of a larger body of work that I've been doing with Sina. You guys, some of you may have seen or heard of his gigantic journal paper comparing a whole bunch of online off-policy prediction methods. This is sort of a smaller sub-question that stemmed from that work, and I'm going to take a slightly closer look at it. And so I'm going to warm up a little bit and go through a derivation of importance sampling, partially just so I can become a little less nervous before I start showing you guys the actual results, but also I think it's important to kind of see where we're coming from, how this all starts. And so we'll get into it. So the idea of importance sampling, it is a sampling method. We have some samples coming from a probability distribution B. In reinforcement learning, we call this behavior distribution, but this is actually more generic than reinforcement learning, and I'm going to speak of it in a more generic sense. But to keep notation smaller and simpler, I'm going to call this probability distribution B. And the idea is I want to estimate an expected value, expectation over a different probability distribution, pi, but using samples that I drew from B. And so to do that, first I write out the definition of an expectation, quite simple. Each of the samples I receive, I multiply the value of that sample times the probability of observing that sample under pi, because this is an expectation, under pi, or over pi, or through pi. Anyways, and I multiply it by 1, where 1 here is B, the probability of observing the sample x, according to B, divided by the same thing. So I haven't done anything interesting yet. I take the numerator, swap it out, still haven't done anything interesting, but this is the importance sampling ratio, and we're going to call it rho. And moving forward a little more, since all I've done is multiply by 1 so far, but I did lots of steps to get there, we can now look at x times rho of x as its own random variable, and we're finding this sum over a different probability distribution b, and so we can write this as another expectation, but in this case, the random variable is x times rho of x, and the distribution here is B. And why that's important or interesting is because as I'm receiving samples from the probability distribution B, I can actually evaluate or estimate this expectation. I couldn't estimate the first one because I didn't have the probability distribution pi to receive samples from. So that's importance sampling. And let's look at how we're going to use it. I know I promised gradient TD methods, but let's start a little more simple and just look at off-policy TD0 and see how we can use the importance sampling ratio. So that's this row again here. And this was the original way that it was introduced in the literature, and that is because R here is according to the behavior policy, and the value function at the next time step is according to the behavior policy, so we have to correct both of those. However, we can also choose to correct this other value function. Up until this time step, at this time step, given my entire history of interactions, this value function here is a constant. And so I can multiply it by rho, and that's not biasing anything, or at least so we think, and I will go into that a little more in detail in a moment. But there are several papers that have used both. There seems to be some cutoff somewhere between 2001 and 2011. We decided that this was a better idea, but as far as I can tell, no one's actually talked about it or said why it's a better idea. We just switched over to it, and so that's kind of the point of this talk is it a better idea? And so I ran a very simple, quick experiment. This is tabular, small Markov chain, like 8 states, very simple, and I'll get into more details of that in a moment. But just running this simple domain, this simple experiment, I noticed this huge difference between the two methods, which made me start questioning whether or not one of them is actually biased, because it certainly looks that way. And so analytically looking at it, I took the expectation of both, distribute this expectation operator over the minus sign here. That's all that happened here. And notice these two terms are exactly the same, so it's equivalent up to that point. But looking at these two, we have to ask if these are equivalent. As I mentioned a second ago, but I'll mention again, this is actually conditioned on my entire history of interactions. So because this is conditioned on the whole history of interactions up until time t, and this is the value function at time t, this is a constant, so it just comes right out of the expectation in both cases. This expectation right here over rho evaluates out to this. These cancel, so I'm just looking at the sum over pi, which is 1, because it's a probability distribution. And so these things are equal in expectation. And that's good. Except we still have this result that shows that they don't look like they're very equal. And so a little more details on the experiment. What I did here is I swept over a lot of step sizes, and I chose the step size that minimized the area under the curve for both of these. So in this case, this was the step size that was chosen. If I run it again, but run it for 10 times the number of steps, and then pick a new step size that minimizes the area under the curve, we get, notice, notable difference, about half of the distance between these two lines, and also a smaller step size. Multiply by 10 times the number of steps. Again, pick a new step size, and it picked an even smaller step size, and do it again, and these things start converging towards each other. A simple experiment to test this would be to actually have a scheduled step size that decreases with time, but I haven't implemented that yet. That's on my to-do list, I suppose. Okay, so that was the simple case. Any questions up until here? Because that's sort of setting the scene for what I'm doing. Yeah?
What did you mean by that left term was independent of, was dependent on the history?
Yeah, so here. So the value function at time t depends on all of the state, actions, rewards, next states that I've received all the way up until time t.
Okay, so this is an estimate.
Right, exactly. So the value function here is an estimate.
And on the right side it's independent? That's what you said? Or?
On this side is still the same v, and so it also comes, oops, oh man, it also comes out of the expectation the same way, because it is a constant with respect to the history up to this time point.
But the two value functions would be different because the grades are different.
That is true, but there should be the same in expectation here. And so they're going to be different actualized value at this current time step, but they're in expectation they're the same at this current time step. I think I saw a hand here.
Yeah. Was I supposed to notice or care about or pay attention that the blue line is much smoother?
No, I hadn't thought about that. You're right, it is much smoother, and I will talk about variance here in a moment, so that'll probably cover that. In fact, I will talk about variance now. Oh good, it's going to work. I created a little graphic here on the left side. We have samples drawn from the behavior distribution. On the right side, we're taking those exact same samples, but multiplying them by the importance sampling ratio. I chose a target policy so that both of these, the behavior policy has mean 0. I chose a target policy that's different, but also has mean 0, just so that this is a sensible graphic. And looking at samples drawn from these, we notice that the importance sampling corrected distribution has way higher variance. And not only that, but a lot of these are very small updates, and a lot of these become huge spikes. Which makes learning very difficult, especially when you put this in the TD error, because the TD error is your learning signal. It tells you how wrong your predictions are. And if this has these huge spikes in information, that can be really hard to learn from. This is all kind of a hand-wavy argument that says variance is bad. Not totally bad, but a little bad in this case. And so we can try to control that variance. Chris has a cool paper out about doing this with in-step returns, and the idea is we have these control variants, they control the variance, or control variance, they control the variance. And the way they do that is you have some stochastic process x. We add some constant times the bias removed version of another stochastic process, and we add that to the original stochastic process, and this could reduce the variance. And that could is these two things need to covary in some way. And so a little bit of intuition about this is if I have some amount of variance in x and some amount of variance in y, these things have some covariance. If I subtract out the variance that's shared between the two of them, then I could decrease the variance in x, which is also kind of a hand-wavy argument, but we'll move on with it for a little bit. So here's sort of a graphic that shows what I'm talking about. You have some constant c, this is some parameter you get to choose, and you have the variance of our new stochastic process, x, and the variance here is decreased whenever c is chosen such that it's below this line. This line is where you have equal variance, where you haven't done anything interesting at all. Say, for instance, when c is 0, you'll be here, actually. And if you choose c less than 0 up until this point, then you will be decreasing your variance in some way. And so if I choose x to be this, which is my TD error here with rho not on v, choose y to be rho times v, and choose c to be -1, then I can derive this. So what I did here was replace delta with the value of delta. Notice here we have an expectation over the behavior policy, the samples that we're receiving. So rho is inside that expectation, so that becomes an expectation over pi. And as we discussed earlier, the expectation of v with respect to pi is v. Moving forward, I distribute this -1 over here. We end up there, cancel out those two v's that are being subtracted, undistribute the rho, and now I'm back to the other TD error term. And so the point of this whole exercise was just to show that I can write the fully corrected TD error term with respect to just the TD target being corrected, and you can interpret this as a control variate, which means that this might be reducing the variance. And I have some qualifications there. There are certain situations where it's going to reduce the variance. I left that out of this just because it adds more to the talk, and it wasn't super important because I think the empirical results kind of motivate it, and I don't fully understand it, so I don't want to say too much. Great. Any questions from there? Yes?
Should we now show that delta rho v are correlated?
Right. So the conditions are that delta and rho times v, these two random variables, have to be correlated in some way. And specifically, c has to be set so that they're minus this correlation divided by the variance of the TD error. And so, right, we would have to show that. I didn't choose to do it analytically, but I will do it empirically. And I've got clicking. OK, any other questions? Cool. So now the gradient TD placements. I have this slide. Everything is really washed out. The purpose of this was for me to stop and warn you guys that I'm putting a lot of equations on the screen all at once. You don't have to read through them. You don't have to memorize them. You have to commit them to heart. These are the updates for gradient TD methods. I'll point to, with arrows and circles, the things that are important here. I just didn't want to wow you guys with a bunch of equations and make you think that you had to read them. So anyways, these are the update equations for gradient TD. The first three up here are shared between both methods. Then TDC has this update for its primary set of weights. GTD2 has this update for its primary set of weights. I say primary set because both of these are two timescale methods, meaning that they maintain two sets of weights. You have some hidden weights, H, and primary weights, W. Notice that TDC, if you ignore all of this and just look at this part, is exactly the same as TD0. We just add some gradient correction term here, and that's the same gradient correction term in GTD2, but that part of the learning rule has changed. Those are the interesting bits. We have rho in here 3 times for each method. This only shows 2, but there's another one that's implicitly inside the TD error right here, because that is defined in terms of rho. And so each one of these methods has 3 different rho placements, leading to 8 different methods. And showing graphs with 8 methods on them, especially methods that differ by only a very small movement of one variable, is kind of difficult. So I created a little code to explain each one of them, but that's also confusing. So on every single slide that has results, I'm going to have this code. I'm also going to have a little cheat sheet to remind you what the code means. So up here at the top, you'll see zeros and ones. 0 means you're correcting everything. You can imagine this like a precision knob, where 0 is not precise at all. I'm just correcting all of the things. And maybe I'll accidentally correct the thing I'm supposed to correct. And a 1 means I'm being a bit more precise and I'm correcting just the thing that needs to be corrected because it's actually coming from a different distribution. And so we have our update for H, the hidden weights. It has a rho right here because that's a random variable. It depends on something that happens on the next time step. This is a constant with respect to the current time step, and I could choose to correct it with rho or not. Likewise, here, this is the TD error, same thing I showed you earlier. So I can correct the whole thing, which is what this is doing, or I could correct just the TD target part of it. And another TD error, same thing. The reason there's 2 TD errors in this method, I don't want to back click all the way, but there are 2 sets of weights, and each set of weights depends on the TD error. And so I could treat those as 2 different TD errors, and each one could have its own placement of rho. So that's why there's 2 in this one. GTD2 has the exact same update for H, so the same set of rho placements there. Has the same TD error for H, so the same set of rho placements there. But it has this update for W, which has rho here. And this is necessary because xt plus 1 depends on the next time step, so I have to correct that. This thing right here is a constant on this current time step with respect to the current time step. But I could also correct that as well. I didn't go through the steps to show analytically that this is unbiased or that this is unbiased, but they are, except in 2 cases for each algorithm. this TD error right here, if rho is correcting just part of the TD error and I have a rho here, that's actually not necessarily unbiased. So realistically, I maybe shouldn't have compared with that method, but I did anyways because I just did a whole spitball of a bunch of tests. So yeah, that was just a little disclaimer that that's not necessarily unbiased. So the experiments I ran is on this environment called collision, also known as chicken. The idea of collision is we start in one of these 4 states with equal probability, and we move right. As we get to these 4 states, we have a choice of either going back to one of the first 4 states or continuing to move right. If I move right all the way, I hit the wall, and I get a reward of 1. And the idea is, imagine you have a robot, tons of sensors, tons of GVF predictions, Horta predictions. One of the predictions that might be useful is, if I keep going straight, when will I hit this wall? Or how long until I hit this wall? And that's what this question is answering. How long until I hit that wall if I keep going straight? So the target policy is go towards the wall all the time. Behavior policy is in these right 4 states, retreat with 50% probability in each of those states. Meaning I only hit this state once every, like, I don't know, 6% of the times, something like that, 6.125% of the times. And to start, very simple, I'm just doing a tabular state representation. And we get some interesting results doing that. Each of these kind of clumps of lines has 4 lines in it, and I circled the thing that separates the lines. So in this case, in TDC, the thing that separates it is the TD error specifically for W, not the TD error for H, which is interesting. And in this case, for GTD2, it's the TD error for H that separates the 2 of them. I don't have a lot of insights as to why at the moment, but this is an interesting result, and you should admire it for a sec. Okay, I was actually a little disappointed with the result, though, because of these clumpings of lines, and I really thought that there should be a larger difference, so I thought maybe I would try to break it. And so I tried to break it by using this feature representation that Sina used in his paper, this big binary encoder. So the key features here is there are 3 features that are always active, 3 that are always 1, 3 that are always 0, and you randomly pick which 3 are active on every single run for each state. So each run has a totally different representation for each state, but no state has the same representation. You make sure there's no overlap there. So some of these are really easy to learn. If I just keep generating these randomly, some of these are super easy to learn from. Some of them are much more difficult. So that leads to a lot more variance. But otherwise, this graph actually looks no different than the first one I showed you, other than just the additional noise I added. So that also wasn't particularly more interesting. But if you look at the second step size, so remember there were 2 sets of weights, this hidden set of weights and this primary set of weights, and each one has its own step size, so it makes it a 2 times scale problem. There is something that's kind of, there is something that's kind of hidden behind the scenes here. This is the sensitivity curve for that second step size, and notice even though all 4 of these and all 4 of these are together on the learning curve, on the step size sensitivity, they actually start splitting up and they start pairing off. And the thing they pair it off on is this update for H. So no matter where I placed the row in this update for H, they seem to still pair off and do exactly the same. GTD2 still looks rather uninteresting. Even here, it still has 4 methods that are together, clumped together, and 4 methods that are clumped together on the other side. So I tried to break it again. And so going back to the collision problem, I changed the behavior policy down here so that it's even more off policy. So rho has even higher variance. So I thought maybe adding variance here instead of through the feature representation to make things more interesting. And for TDC, it still really did not. We still kind of have 4 methods that cluster together. Maybe something interesting is happening here. 2 of those 4 are a little bit worse than the other or better than the other. And it's still split over the same placement of rho as before. But GTD2 became a lot more interesting, and things started segregating a lot. And sort of in the same vein as earlier, we have things that are pairing off here. It's kind of hard to tell what's pairing off there. And it looks like it's roughly pairing off over this update for H, which is also a little interesting. And finally, just to keep trying to break it, I went with a problem that is known to break things, Baird's counterexample. It's a counterexample because it is counter to the example of TD learning. And so it's meant to break things. It has a hard feature representation, has high variance due to the importance sampling ratio. And it did break things a lot. And some of these work really well. Some of them work rather terribly in comparison. I don't have a lot of insights from this because Bayer's counterexample breaks so many things all together at once. It's kind of hard to determine what thing broke it. And so my goal, the point of having done this is I can now kind of look into the future and say there is hope that something interesting might come from this project at some point because things are interesting on this example. Yeah?
Which one is broken here?
You might consider these two to be broken, here and here. These two to be broken. This one looks really cool.
In the textbook, the graph that they show, when they discuss the counterexample, it achieves an RMS VE of 2.
Mm-hmm. Yep.
Say that it's doing the right thing.
Which these two.
Minimizing the mean square projected Bellman error.
That is true. However, but it's not getting the same value error. So all of these, if we did the mean square projected Bellman error, converge to 0. Mean square projected Bellman error, and that's great.
So maybe that was specific to a representation. And over here, are you changing the representation?
What was, no change to the representation.
So how is it getting less than 2?
That is a great question. I have no idea.
So maybe the ones that are biased are the ones which are actually achieving a lower RMS VE.
Not in this
That is not what
case.
we're minimizing, right? These algorithms are not minimizing RMS VE.
Right, that is true.
And if they get so the objective that they're minimizing, if they minimize it to 0, RMS VE is 2.
Oops, sorry. I'm tired of you. I moved on. No.
Yeah.
Yeah, no, that's a good point. It could be, in fact, that these aren't actually broken, and that these two are doing the right thing in minimizing the mean square projected Bellman error, and that these things are not doing as good of a job at minimizing those, although they do all converge towards 0 mean square projected Bellman error. So it's unclear. It is unclear why one of them might have higher RMS VE than the other.
So, okay.
Yeah, Chris?
I remember that those curves didn't actually plateau yet. If you let it run until like infinity, they do eventually reach 0.
These ones?
Yeah, like they will eventually still reach 0 if you let it run long enough.
Yeah, that's definitely likely. Yeah, especially since I'm choosing a very short number of time steps. I'm picking the alpha that minimizes this area under the curve for the short number of time steps. So most of the time, this is choosing a rather aggressive alpha because it really wants to minimize or to maximize how quickly this learns in the early stages.
But if the Bellman
So-
error is 0, how can it go down further?
The problem is fully representable with the weight vectors that they provide.
But the objective that is being minimized is 0.
When
They should have matching.
and when a loss function is 0, it doesn't necessarily mean it's actually done learning too. Like loss functions actually could go below 0. I don't know if that's true. I guess that's not true of the mean square projected Bellman error, so I guess that's not interesting. So never mind.
Yeah, like in the book it says it stops at 2, but then like they also say that it is still continuing to decrease. They just didn't show it.
All right.
Mm. So this is another example where like a step size schedule, for instance, would be an interesting thing to try. Let this run for 1,000,000 time steps with a decaying step size and see what happens. But that's all I have. So thanks for your time. Any questions? Yeah, Matt.
So I'm just wondering where state action values play into the mess of all this.
Yeah.
If I remember correctly, the 2 papers you cited from Doina were on
State action values.
functions,
Yep,
and
you
I
are
could
correct.
Imagine, and it seems like it's the case from the literature that algorithms for state value functions don't necessarily work for state action value functions. And I'm wondering if you've done any experiments.
I have not done any experiments. I did, as I was preparing these slides, panic a little bit as I was looking at Doina's papers and realizing they were for state action value functions. And then realizing that actually, I think what we're doing here is reasonable. And when I say I realize this, I actually mean Sina kindly pointed it out in the Slack. That what we're doing here is totally reasonable. In Doina's paper, she actually doesn't correct R because she doesn't have to, because that's coming from the behavior policy, which was the target policy on the last time step. So she's only correcting for the value function Q in her case there. So in a sense, if I were to do state action values, I'd actually, I guess, have 3 options here of places where I could be correcting. Since R would be also a constant in the state action value case with respect to the current time step. So I could do just on the value function in R, or on the whole TD error. And I haven't tried that, so that would be interesting to take a look at.
Yeah, because it seems like it may fix some of the. not necessarily fix, but it
Mm.
would change your initial results.
Yeah.
It's, simple.
Yep, I agree. Alex?
Were you able to find any like consistencies in the important sampling correction term placement? Because like it's kind of hard to see from a quick glance of like over the 8 which were like consistently good amongst your different placements.
Yeah, let me pull one of those up real quick.
Yeah, who did it right of all these people?
Well, Sutton, because he's on all of the papers. So Rich did it correct. It looks like the same things are circled in all of the experiments I've done so far, as whenever things clearly just have obvious differences between them, it's always these same two things that are circled. So for TDC, it's the ratio placement on the TD error used in the primary weights, and on GTD2, it's for the TD error in the secondary weights. Yeah.
And for these, did you check whether the update is biased or unbiased?
For both of these, it is unbiased. And for that matter, there are only 2 out of these 8 methods that are biased in both cases. And so those just naturally still clump with the other ones, which is why I ended up leaving them in the plots, because empirically there seemed to be no obvious sign that anything was biased. Yeah.
So as a follow-up to that, so did you check if the extra row term is acting as a control variant in these updates?
I haven't yet. I believe that to be the case, just kind of from a cursory glance. I did take a quick look at it and didn't write it all the way out, but it looked like the thing that they were being the thing that was actually the control variant, the thing that was supposed to co-vary with, was a little nonsensical. That these two things varying together didn't quite make a lot of sense. But yeah, I haven't gone any further with it, but it is on my list of things to do as well. And to fully answer your question, Alex, this is the only insight I've come by so far with the experiments, but this is a really simple MDP. It's a pretty simple representation still, so I'm continuing to throw things at it to see if I can break it more and then figure out which thing was the tipping point, to see if any more insights come out of it. Yeah. Any other questions? Yeah.
Have you tried actually writing down the second moments of the samples you get from the distribution? I think that's way more illuminating to see which one is like closer to 0 and its second moment.
Good question. I have not tried actually writing out analytically the second moments. I have empirically tested the variance of many different things, including just the entire update or the variance of the TD error. But those, sorry, I keep playing with this and moving around slides. Looking at it empirically, it seemed like some of them were definitely lower variance, but I didn't look at the graphs for very long because I just generated them, didn't feel comfortable enough tossing them in the slides. But yeah, that is something I'm continuing to work on, actually looking at the second moment to see what's happening. Yep, great question. Anyone else?